Welcome to the next lecture in elementary statistics, where we're going to cover section 5.2, the addition rule and complements. We're going to use the addition rule for disjoint events, use the general addition rule, and then compute the probability of an event using the complement rule. Use the addition rule for disjoint events. Two events are disjoint if they have no outcomes in common. Okay, so that none of the outcomes for one event can be the same. So an example of a disjoint event would be if we're rolling a die, if one event said you'd roll an odd number and the other event said you'd roll an even number, notice that a number cannot be both odd and even, so those two events are disjoint. They have no outcomes in common. A number is either even, so it would be in one event, or odd, it would be in the other, but there's no number that's odd and even, so there's no common events. And that's what disjoint means. They are mutually exclusive events. They have nothing in common. The addition rule for disjoint events says if E and F are disjoint or mutually exclusive events, then the probability of E or F, now this is important, E or F equals the probability of E plus the probability of F. Okay, this connector or is important. If we said E and F, then we're looking for something that's a member of both E and F, and that's a different situation. Okay, notice if we have even more than two events, as long as each of the events is disjoint from all of the other events, then this addition rule works as well. So what we're saying is, as long as, in this case, as long as E and F and G and any other added sets or events are mutually exclusive, then the probability of E or F or G is equal to the sum of the probabilities of each. So this addition rule doesn't just work for two events, it works for as many events as there are, as long as there are no members in common for any of the events, across any of the events. We often draw diagrams of events using Venn diagrams, which you can see down here to the bottom left. A Venn diagram represents events as circles inside a rectangle. And the rectangle is just as important. A lot of people forget the rectangle. They just think of the circles inside. The white box or rectangle represents the sample space. So in this case, in this diagram, notice the sample space includes 3, 4, 5, 6, 7. That's up here in the white box and outside of either circle. But the sample space also includes the two circles, which is 0, 1, 2 for event E and 8, 9 for event F. Okay, so the sample space would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. It would be all of those. And then event F would just have 8 and 9 as possible outcomes, and event E only has 0, 1, and 2 as possible outcomes. For example, suppose we randomly select a chip from a bag where each chip in the bag is labeled 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9. Let E represent the event, choose a number less than or equal to 2, and let F represent the event, choose a number greater than or equal to 8. So we can see automatically that these two events are disjoint. There is no number that is less than or equal to 2 that is also greater than or equal to 8. And so that's why these circles do not overlap. It is possible in a Venn diagram that the circles would overlap, and then that overlapping outcome would be in the intersection of the two circles. Okay? So we have two disjoint events, E and F. So the probability of E is very simple, right? We know that the sample space has 9 members, 0 through 9. E has 3 members. So the probability of E is the number of outcomes in E divided by the number of outcomes in the sample space. So we get 3 over 10 or 0.3. Similarly with F, we get the number of outcomes in F, which is just 8 and 9, or 2 members. And then, of course, the number of outcomes in the sample space. I think I said 9 a minute ago, but of course it's 10 because we have 0 as well. There are 10 digits in the sample space included in the entire white rectangle. So we get 2 out of 10, which is 0.2. If we wanted the probability of E or F, remember here we could also do this just the natural way. What members are in E or F? Well, that's 5 members. And what members are in the sample space? That's 10 members. So the probability of E or F is 5 out of 10, or 0.5. But we could also, seeing that this 0.5 is equal to the sum of the individual properties, and this is the addition rule for disjoint events that we just talked about. So we could have found the probability of E or F by just summing the two probabilities together, the probability of E plus the probability of F, and you can see that these numbers are indeed the same. So as I mentioned, we can have more than 2 events. We can use the addition rule for multiple events beyond 2, as long as they're all disjoint. And now we have 3 events, E, F, and G. E and F are the same as before, so you see the probabilities that we calculated before. We can see that G is also a disjoint event from E and F, and it has 2 members in it, so its probability is also 0.2. So if we wanted the probability of E or F or G, we would simply add these 3 probabilities together, 0.2 plus 0.2 plus 0.3, and we'd get 0.7. So these are pretty straightforward and simple idea that as long as events are disjoint, we can calculate each probability individually, and then if we want to calculate a combined probability of all the events with the connector of OR, then we just simply add those probabilities as long as they're disjoint. Benford's law and the addition rule. Our number system consists of the digits 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Because we don't write numbers with a leading 0, such as 0, 1, 2 for 12, the first significant digit in any number must be 1, 2, 3, 4, 5, 6, 7, 8, or 9. It does not include a leading 0. Significant digits do not include a leading 0. It's pretty simple and logical to assume or to think that each digit would appear with equal frequency. So we think that each digit has a 1/9 probability of being the first significant digit. But this is actually not true. In 1881, Simon Newcomb discovered that digits do not occur with equal frequency. The physicist Frank Bedford discovered the same result in 1938. And after studying lots and lots of data, he assigned probabilities of occurrence for each of the first digits, as shown in Table 5 at the bottom of your screen. The probability model is now known as Benford's law and plays a major role in identifying fraudulent data on tax returns and accounting books. Okay. Now, these are, would you say that these are actual probabilities or approximate probabilities? Well, since he studied lots and lots of data, he made lots of observation, what we're looking at is really relative frequency. So these are not actual probabilities that one will occur 0.3% or 30% of the time, but the fact that it is likely to, or an approximate probability. Remember, when we observe things and we do it by counting and observing, those are approximations of probability versus when we use the classical method where we actually calculate the probability because it's equally likely. So based upon Benford's law and the addition rule, verify that Benford's law is a probability model. Well, remember there's 2 rules. The first rule says that every probability has to be between 0 and 1, and we can see that that is indeed true. The second rule says that the sum of all probabilities is 1, and we can add the probabilities from 1 to 9 up together, and we will indeed get the number 1. So table 5 does represent a probability model because it meets both of the rules. Use Benford's law to determine the probability that a randomly selected first digit is 1 or 2. Well, this is what we've been doing. Since 1 or 2, you can't select a number 1 that is also the number 2. A number is either 1 or it's 2 or it's neither. So these are mutually exclusive events. The probability that a digit is 1 is mutually exclusive from the probability that the digit is 2, because you can't have a number that is both 1 and 2. Okay, so the probability of 1 is 0.301, the probability of 2 is 0.176, and so we just add those together and we get 0.477. Part C says to use Benford's law to determine the probability number that a randomly selected first digit is at least 6. Whenever you see at least, at most, greater than, less than in probability, you have to change that to a statement that is an exact statement, not an equality. So, and this is one that a lot of students actually get incorrect because they think, well, if it's a digit has to be at least 6, a lot of students sometimes will go thinking least is less than, so they'll go 1, 2, 3, 4, 5 and calculate those probabilities. Notice that if a first digit is at least 6, this means it's 6 or more. 6 or more. At least 6 means that the digit is 6 or more. So what we're talking about here is the probability of 6 or 7 or 8 or 9. Okay? And since a number cannot be 6 and 7 and 8 and 9 at the same time, these are mutually exclusive. So we simply add up all of the results and we get 0.222. Okay? So let's look at another example. Here we're looking at a deck of cards. Okay, suppose that a single card is selected from a standard 52 card deck, such as the one shown in the figure below. So if you're not familiar with the standard card deck, there are 52 cards, and they are in 4 different suits. We call these suits: a black ace, a red heart, a black club, and a red diamond. Those are the suits. Spades and clubs are black, hearts and diamonds are red, and then the same cards appear in each of the suits. So in each suit has an ace, which is sometimes considered the high or low card. It has numbered cards from 2 to 10, and then 3 face cards: a jack, a queen, and a king. And you see those same repetitive cards in each suit. So there's 13 cards in each suit, 4 suits, giving us 52 cards. All right. So compute the probability of the event equals drawing a king. Well, we know that there are 52 cards in the deck, so this is the size of our sample space. We know that there is a king of spades, a king of hearts, a king of clubs, and a king of diamonds, so there are 4 kings. So this is a really easy calculation. Since the deck has 52 cards, this is our sample space. The number of outcomes in our sample space is 52. And since there are 4 kings, the number of outcomes in our event are 4. King of hearts, king of diamonds, king of spades, or king of clubs. So our probability is simply 4 over 52, or 1 over 13, or 0.0769. Compute the probability of the event E is drawing a king, or F is drawing a queen, or G is drawing a jack. Since we're only pulling one card, a card cannot be a king, a queen, and a jack at the same time. So these are all 3 mutually exclusive. So all we need to do is we've already found the probability of E for drawing a king. We need to find the probability of drawing a queen and the probability of drawing a jack, and then add those 3 together. Well, drawing a queen and drawing a jack is similar to drawing a king because there are 4 queens, jacks, and kings in a deck. So the number of outcomes in E is the same as the number of outcomes in F, which is the same as the number of outcomes in G, which means that the probability of E is also equal to the probability of F, which is also equal to the probability of G. So we just simply add that. We could have multiplied it by 3, but here we add the probabilities because it is the addition rule, and I don't want to kind of confuse you. So we get 113 plus 113 plus 113 equals 3 over 13, which equals 0.2308. So these may seem a little confusing at first. Do a couple of these and they'll get easier. It's a really simple idea and simple concept and simple formula to calculate probability, at least at this point of the game. It gets a little more complicated soon. So our next objective is to use the general addition rule. And this is for any set, whether it is disjoint or not. And so for any two events, E and F, the probability of E or F equals the probability of E plus the probability of F minus the probability of E and F. And this may not be quite clear at first, but let's look at an example. So if we look at this Venn diagram of rolling a die, a single die, and so we can see the numbers inside of the rectangle are 1, 2, 3, 4, 5, 6. That's our sample space for rolling one die. Our event E is to roll an even number. So in the outcomes in E are 2, 4, or 6. If event F, the circle here to the right, is to roll a number greater than 4, that includes two numbers, 5 and 6. Notice that the 6 is in this middle section, or the overlapping, or the intersection, E and F, for members that contain both. So if we just use our classic method, we can see that that the probability of E or F are all the numbers inside the two circles, which is 1, 2, 3, 4, out of the total possible numbers in the rectangle, which is 6. Okay, so we know how to do this by just looking at it. But the probability, when we think the problem, not the probability, sorry, the problem when we look at these separate, if we just added up, notice if we added up, if we found the probability of E, just E, we'd have 1, 2, 3 members over 6, plus the probability of F would have 2 members over 6. And if we added those probabilities together to try to get probability of E or F, we would get 5 over 6. And that's because we're counting the 6 in both of these individual probabilities. We're not at the probabilities yet, but and so that's what this formula does, is it takes out the double counting. And so what we're minusing is how many members are in both, so that we don't count them in both, if you will. Okay, so we can see that the number in E is 3, plus the number in F is 2, minus the number in E and F, which is 1, gives us the actual number without double counting of what's in E and F, which is 4. 3 plus 2 is 5, minus 1 is 4. So that's what this does. Notice this formula is really the numerator of a probability. If we divide the bottom of each of those terms, both sides of the equation, by the number in the sample space, we actually get this formula up here. The probability of E union F equals the probability of E plus the probability of F minus the probability of E intersection F. So here you have it in mathematical symbols of union, which is or, and intersection, which is and here you have it in terms of words. And so here we can add these in there, and we get 3 over 6 plus 2 over 6 minus 1 over 6 equals 4 over 6. When you're doing these kind of complex or multiple steps probabilities, leave it in fraction form and don't reduce it, because if you reduce this first one, and even if you reduce the second term, then you're going to have to go back when you're trying to add fractions and find common denominators. Because your denominator is the sample space, the number in the sample space, you'll already have a common denominator as long as you don't reduce intermediate steps in the problem. And again, in words, the probability of E or F equals the probability of E plus the probability of F minus the probability of E and F. So you should know this in words, and you should also know it in terms of math operators, where union is or and intersection is and. Okay? And again, what's happening is here is we're just stopping the double counting. If we just added the probability of E and the probability of F, we're actually counting the 6 twice in each of those, once in each of those probabilities. So the general addition rule, we can look at this, another example here. If we do the direct counting, which is what we just did in that last example. So here we can see what is inside of E and F. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 members inside of E and F, and there's 2 members outside. So in the sample space, there's 10. So the probability of E or F is the number in E or F, which is 8. And the number in the sample space is 10. So we get 8 over 10, or 4/5. Note the probability of E or F does not equal the probability of E plus the probability of F when they overlap, because of that double counting phenomenon. Okay, so the general addition rule, just make sure you take care of the double counting. You can do a direct counting when you're not physically double counting, but if you did the probability of E plus the probability of F, you would get it wrong. So this is something we don't do. It's not just the probability of E and probability of F. However, here's the formula again. Probability of E or F is the probability of E plus the probability of F minus the probability of E and F. How many members are in the intersection? In this case, 2 over 10. So we see that we get back to just what we get by direct counting. Sometimes you're not going to be able to count like it is easy here. So don't think you can just always use this method. You need to know this formula, again, in words and in mathematical symbols. So computing probabilities for events that are not disjoint. Okay. Suppose a single card is selected from a standard 52 card deck. Compute the probability of the event E equals drawing a king, or F equals drawing a diamond. Well, let's use our formula. If event E is drawing a king, how many kings are there in a deck? We know the sample space, the number in the sample space is 52. We did this already. So the probability of E, drawing a king, is 4 over 52. The probability of drawing a diamond is the number of diamonds in a deck over 52. And remember, each suit, there's 4 different suits. 52 divided by 4 is 13. There's 13 cards in each suit. So for the probability of F, we have 13 over 52. But what about E and F? Here we're looking for a king that is also the card that is a king and a diamond. A king and a diamond. How many king of diamonds are there? In this case, there's only 1. Okay, so we're looking for the probability of a king plus the probability of a diamond minus the probability of a king of diamonds, a king and a diamond. And so again, there are 4 kings in the deck, there are 13 diamonds, and there's 1 king of diamonds. So notice here, when we're counting the 13 diamonds, we're counting that king twice. That's the duplicate in both of those. And so we get a probability of 4 over 13. This is what's called a contingency table, or a two-way table, because it relates 2 categories of data. The row variable is the marital status, never married, married, widowed, divorced, or separated. The column variable is gender, males, females. This also represents U.S. residents who are 15 or older. Each box is called a cell. Like each entry in an Excel spreadsheet, each box is a cell of data, a cell of titles, etc. So using this data for Americans who are 15 or older, let's go through some calculations. Determine the probability that a randomly selected U.S. resident 15 or older is male. Okay, so here are the male categories. Remember, when we're talking about these probabilities, we're talking about the relative frequency based upon the data given. So what we need to do is figure out how many males there are, and then figure out how many total people were surveyed. So we've got to find a lot of totals. If we add up all of the columns under the male, we get 126.9. If we do the same thing under the female, we get 133.2. And if we add those two totals together, we get 260.1. So if we're trying to find the probability that a randomly selected resident is male, we would take the number of males divided by the total number of observed males divided by the total of observations. And here we get 0.488. Okay? Determine the probability that a randomly selected U.S. resident 15 or older is widowed. Okay? So now we need to figure out the total count of people that were widowed. Here there's no gender, so we're just looking for widowed. So we're going to add up the total number of widows, males and females, which is 15.2 million. We're then going to divide that by the total of observations, or our sample space, 260.1, and we get 0.058. In part C, notice we're doing the probability that a randomly selected U.S. resident is widowed or divorced. Okay, widowed or divorced. We already found widowed here. Okay. Now we're assuming that there is no overlap, okay? That you fall in one of these categories, not the other. Like you can't be widowed and divorced, okay? If you got divorced once they die, you're not widowed, okay? But we're assuming that obviously people could have multiple marriages and have fit in most of them. Or more than one, I should say, not in most, hopefully. So that we already have the probability of widowed. So let's find the probability of divorce the same way we did before. 12.1 and 16.1 gives us 28.2. 28.2 million people divided by 260.1 gives us 0.108. Okay. Because they are mutually exclusive, widowed and divorced, we don't have any, these are disjoint events, widowed or divorced. So we can just simply add the probability of the widowed plus the probability of the divorce, and here we get 0.166. But we have a problem with this calculation. Each of these numbers, 0.058 and 0.108 that we have in this calculation, we rounded. If you did this calculation yourself, you would see that we rounded to 3 decimal places. And so this is a rounding problem. This is a rounded answer. So we used rounded data inside the calculation, which is not really a good idea. Really what we should have done is added up all of the widowed people, 15.2, plus all of the divorced people, 28.2, and then divided them by the total number in the sample space, 260.1. When you do that, you see we don't get 0.166, we actually get 0.167. So in general, it's a good rule of thumb in math to always use the data the data given for your answers as much as possible to avoid such a rounding error problem. Finally, the last one is to select determine the probability that a randomly selected U.S. resident is male or widowed. Male or widowed. Okay, so here we have the probability widowed, the probability mailed, we have the probability widow, we have the probability male, but notice there are some males who are also widowed. So in this case, we do not have a disjoint events. We're going to have to use the general addition rule, which subtracts out the intersection of those. So we're going to have, for males, we're going to have 126.9 over 260.1. For widows, we're going to have 15.2 over 260.1. And for male widows, which we're going to subtract, it's going to be 3.3 over 260.1. Notice this time I did not use the decimal calculations. I used the actual data given and put it in fraction form. I don't want to try to simplify any of these, although that would be a nightmare with these numbers, but I don't want to simplify them till the very end because, again, I have a common fraction. So when I do all of these, it's 126.9 plus 15.2 minus 3.3 gives me 138.8 divided by 260.1. And I get 0.534, which shouldn't have any, it's still a rounding error because there's digits here, we're rounding, but there's no rounding error caused by our calculations because we're only using given data. Okay? Objective 3, compute the probability of an event using the complement rule. The complement of an event. Let S denote the sample space of a probability experiment and let E denote the event. The complement of E, denoted by E apostrophe, which we actually read as E naught, or EC, which is E, the complement of E, that is the complement of E, with it looks like a C is the exponent, includes all the outcomes in the sample space that are not outcomes in event E. That's why we sometimes call this E naught. Okay. So if you think of an event E as whatever elements or outcomes inside the circle, the complement of E, or E naught, is everything that's outside the circle but in the white rectangular box. Again, E apostrophe can be read as not E or E naught. The complement rule says if E represents any event and not E or E naught equals its complement, then the probability of the complement of E is equal to 1 minus the probability of E. Well, that makes sense because remember all the probabilities inside the box have to add up to 1. So if we take the probability of E plus the probability of everything that's not E, then we're going to get 1. And so the probability of E plus the probability of E naught equals 1. And so we get this formula to find the probability of E naught. This is often used when there are simpler or fewer calculations to figure out what's not the event than to figure out the probability of the event. According to the National Gambling Impact Study Commission, 52% of Americans have played state lotteries. What is the probability that a randomly selected American has not played a state lottery? Well, remember, this is really quite simple. Here we have the event is people who played the lottery, so the complement of that event is people who have not played the lottery, which is what we're trying to find. So the probability of not playing the state lottery equals 1 minus the probability of playing the state lottery, which is 1 minus 0.52, which is how we write 52%, which gives us 0.48. So the probability of randomly selecting an American who has not played a state lottery is 0.48. The data in Table 7 to the right represents the income distribution of households in the United States in 2017. Notice the numbers of households are in thousands. It's always important to look at those, especially if there's any units on here like millions, etc., that we saw in the last example. Compute the probability that a randomly selected household earned the following incomes, 200,000 or more. Well, this is pretty straightforward, right? We have one category which is 200,000 or more. So we're trying to figure out what's the probability of selecting one person from this group of 8,284 thousands. Well, as in all of this, this is our number of observations of the event. We need the sample space, which is going to be the total of this entire black and blue column here. So we first need to find the total number of households. If you add all of these up, I'm not going to write all those numbers out. You can figure that out. You get 120,063,000. Again, remember this number is in thousands, so you'd have to add another 3 zeros to it, which really gives us 120 million, because 120,000 is 120 million. Now we can do our simple probability calculation by the number of event observations divided by the number in the sample space, and we get 0.069. So this says the probability of randomly selecting a household that earned 200,000 or more is 0.069. Okay. The next one is to find the number of households that earned less than 200,000. Okay. Well, notice that this is less than 200,000 is the opposite or the complement of 2,000 or more. If it's not less than 200,000, it's 200,000 or more. So remember that a complement, we're talking about the complement of E here. So this is E naught from part A. And remember that the probability of E naught is 1 minus the probability of E. In this case, I didn't use the 0.069 because we had a rounding error before, and this is a rounded number. So I used the original calculation, 8284 over 120,063, and it actually worked out this way. So there wasn't an additional error that would be caused, but we still should use the original numbers given whenever possible. This is another way of explaining this or interpreting that. If we randomly selected 1,000 individuals, we would expect 931 to have household income less than 200,000. Okay. So this last one is a little tricky. It says at least 10,000, and there's no one in here that has at least 10,000. We start at less than 10,000 and then go above that. But do notice that this is at least 10,000. At least 10,000 means that you make 10,000 or more, right? And so what this is saying is that the opposite of this event F, 10,000, at least 10,000 means 10,000 or more, which is all of these other categories. So F naught, or the complement of S, is less than 10,000. If it's not 10,000 or more, the opposite is less than 10,000, which is our first category. So we can calculate the probability of this first category subtracted from 1 because it is the complement of what we're looking for. So here we get 1 minus the probability of F naught, which is 1 minus 7804 over the 120,063, which gives us 0.935. And again, we could read this two ways. The probability of randomly selecting a household that earned at least 10,000 is 0.935. We could also say if we randomly selected 1,000 households, we would expect 935 of them to have at least income of 10,000, not at least $10,000. Sorry. Okay. So that was kind of a tricky one. A couple of ways that you'll see problems in the text and in real life too. And oftentimes we forget about the complement rule, and the complement makes it so much easier. Notice for this last one, if we had just done it correct, which was 10,000 or more, we would have said, oh, that's the probability of this, plus 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 the probability. Do you see where I'm going? It's a much more involved calculation, where 1 minus 1 calculation is much simpler.